Our next talker, Liz Rice, she will talk about eBPF, which is network-related technology. She's from Isovalent, and she is the Chief Open Source Officer. And let's welcome Liz Rice.
Hi, everyone. Thanks for having me here at Craft Conference. So yes, as has just been mentioned, my name's Liz Rice. I am the Chief Open Source Officer at Isovalent. Isovalent is the company behind the Cilium networking project, which you may have come across, particularly if you're using Kubernetes, as it's one of the options for networking plugin. And Cilium is powered by eBPF and brings that eBPF power to networking. eBPF is something that I've been interested in for a few years now, and it's really the reason why I've joined Isovalent, because there's so much expertise in the company around this space. So I really want to talk today about really why I'm so excited about it and how eBPF is bringing superpowers into the cloud native environment. I'm also, you may have come across me if you're involved in the cloud native world through my role as the chair of the technical oversight committee for the CNCF. So if my name seems familiar, that might be why. All right, so I think it's traditional to start a talk by explaining what it is that I'm talking about. So the standard way when you have an acronym name like eBPF is to spell out what that acronym stands for. And in this case, it's Extended Berkeley Packet Filter. And I could explain why it's called Extended Berkeley Packet Filter, but to be honest, the name is kind of historical and not necessarily that helpful. So if you really want to know, you can ask me about that in the questions later. I want to concentrate on what eBPF does. And what it does is it makes the kernel programmable. It allows us to write custom code and run it in the kernel without having to write a kernel module. We can load eBPF programs into the kernel dynamically as we need them. And this is a really big shift. This is different from what we're used to in application programming. Normally, we write application code in user space. So if we have a programmable kernel, what does that mean in I think this is, my slide's gone out of order. I need another slide first. Ignore that. I'll come back to talking about Kubernetes. Right, so what does it mean to run custom code in the kernel? So we're going to have a user space application. This is like normal application code. It runs in user space. But we're also going to write the eBPF code that's going to live inside the kernel. And our user space application can communicate with that eBPF code running in the kernel. The eBPF program is going to run triggered by some kind of event. There are loads of different events that can trigger eBPF code. Could be, for example, the arrival of a network packet. It could be that a particular function call inside the kernel is started or even exited. It could be a function call in user space that's been started. You can attach eBPF programs to those events. You can attach an event to a trace point. So there are thousands of places within the kernel that we can attach these eBPF programs. And whenever that event is hit, our eBPF code is going to get run. The eBPF program has to be loaded into the kernel by something in user space. And as normal, we interact with applications in user space, and that will be where we can do things like print out information that we've obtained from the code running in the kernel. So I think the easiest way to explain this rather than theory is to look at some code in practice. So I have the equivalent of hello world in my editor here. Let me just hide this controls. Okay. So The actual eBPF code itself is written in C. This is going to get compiled into eBPF bytecode that is going to be the code we actually run in the kernel. And this is basically the equivalent of hello world. I'm going to change this to say hello craft conference. So this is a very, very simple program. Whenever we call it, it's just going to create a trace message. That's my eBPF code that's running in the kernel, but I need a user space application to communicate with it and to load it into the kernel in the first place. And this is my Go code. So I'm going to compile that C code into an object file that this Go code is going to load. It's going to load the BPF information from that object file into the kernel. The program we're interested in is called hello. And I'm going to attach it to what's called a kprobe. Kprobe is the entry point to a function in the kernel. I'm actually going to attach it to the function that gets called whenever we run execve. And if you haven't come across execve, it's the system call that's used to execute a program. So every time you start a new program on Linux, execve is the thing that actually says, here is the program I'm going to run. All right, so every time we run a new program on this machine, we're going to trigger that hello application in eBPF, and it should trace out the message. So I've got a make file that will build my objects, and the Go code was already compiled. And I need to be privileged to do this. There's actually a capability that allows you to load BPF programs. You don't actually have to be root, but you do need this capability, this privilege, if you like, the permission to load BPF programs. So I'm just doing it as root. And it wants my password. Okay, so my eBPF code is now loaded into the kernel. And if I make something happen on this machine, it traces out my hello world. And if I run I'll run it a couple more times, so you can see every time the process or a program gets run, we're getting that tracing out. And a few things might happen in the background. And in fact, if I do something in the editor here, that probably will trigger a whole load of events on my server. And you can see information about the process that made this particular system call. That's kind of part of the standard helper function that I used here, the print K. It includes information, some extra information, such as the process that triggered this in the first place. Now, what I want you to really notice about this is that it doesn't matter what process I'm running, it triggers the eBPF program. So anything that's happening on this virtual machine in this case, or it could be across a whole host, anything that happens across this machine is, if it's sharing the kernel, my eBPF program can be aware of it. So this is a super simple example, and it really is just the hello world of eBPF. You can pick up the code for that and a slightly more advanced example that allows us to share a bit more information between user space and kernel space in my GitHub repo. But I hope that gives a little bit of an example of how we write eBPF code, load it into the kernel, and then it can see processes running across that entire machine because it's all sharing the same kernel. So what does that mean if we're in a Kubernetes or a containerized world? So containers all share the same kernel. If they're on the same host machine, there is just one kernel per host. And this is really one of the big differences between containers and virtual machines. Containers are really just processes from the Linux kernel's perspective. So in Kubernetes, all of our application code is running inside containers, inside pods. But there's still only one kernel on that host. That kernel is shared by all the processes and all the containers running on that machine, or at least that virtual machine. Now, whenever the application code running in pods, or in fact anywhere in user space, whenever it wants to do anything, it kind of has to ask the kernel to do it on its behalf. And this is really what system calls are all about. So if you want to open a connection to the network, or if you want to read or write to a file, if you want to create a new process, pretty much anything you want to do, user space has to ask the kernel to do it on its behalf. Pretty much the only thing user space can do without kernel assistance is a bit of adding up. Everything else requires assistance from the kernel. And there is only one kernel per host. So the kernel is involved every time your applications do pretty much anything, regardless of what pod they're in, regardless of what container they're in. The kernel is going to be involved in pretty much every activity that your applications are going to do. So if the kernel is aware of everything that's happening across that whole machine, and if we can insert eBPF programs and attach those to events inside the kernel, eBPF programs can be aware of basically everything that's happening inside those pods across the whole machine. And we can write user space code to communicate with those eBPF programs and bring all that information together in really useful ways. This is how the eBPF-based generation of networking and observability and security tools are being built. We can observe things that are happening across the host. We can even affect things that are happening on the host. For example, in the world of networking, we can have an eBPF program that's triggered when a networking packet arrives, and we can decide where to send that packet inside eBPF, or we can even decide whether to drop network packets. And that's the basis of things like network policy in eBPF networking, like Cilium. So because our eBPF programs are aware of everything that's happening pretty much across the whole machine, we can write eBPF programs to be Kubernetes aware. So the next thing I want to show you is a little bit of a demonstration of how Cilium is aware of Kubernetes identities and how we can tie this into network flows that are aware of these Kubernetes identities. All right, so let's just check I can still see my nodes. KS is my abbreviation for kube control in the kube system namespace. Nodes are obviously cluster wide, so I didn't really need the KS. But if I do KS get pods, we'll see all of the pods that are running in the kube system namespace. And there are 2 Cilium pods here. That's 1 agent per node. So it's running as a daemon set. If you're not familiar with Kubernetes, that just means there is 1 agent running on every node in the cluster. And if I exec into one of these, I'll just pick, doesn't really matter which one I pick, I'll just take the first one. QK94. And I'll run bash. Okay, and reset the screen. And I can look at things like the Cilium endpoint list. So this is the list of networking endpoints that this particular Cilium agent is aware of. And don't worry too much about the details. What I'm really intending to show here is that there's information here about Kubernetes labels, and we can see things like what applications are involved for a particular endpoint. So there's an IP address associated with this endpoint, and there is some Kubernetes information. So because Cilium is keeping track of all of the different networking endpoints across each agent is looking after the endpoints on its own node. So across the whole cluster, we know about all the endpoints across the whole node. And we can tie those together with this Kubernetes information. And if we bring that all together in one place, we can bring together a UI that looks something like this. I would show this live, but it turns out to be a bit of a nightmare trying to manage all the different browser windows. So I resorted to taking a screenshot. I apologize. But I hope what you can see in this screenshot is there are lots of different Kubernetes services running in this example deployment. And we can see how traffic is flowing between them. And we can inspect individual flows in this cluster and look at these flows in the context of these Kubernetes identities. So we can see things like what the name of the service is and what namespace it's in. We can see things like the pod names. This takes networking observability in Kubernetes to a whole new level. We don't have to worry about what IP addresses are involved. We can use the Kubernetes identities. In Kubernetes, IP addresses for pods are ephemeral. They come and go. Every time a pod's created, it gets assigned a new IP address. So having your network observability aware of which pods are associated with which IP address is a massive help. And we can do this, as I say, because eBPF is aware of everything that's happening across that host. So eBPF apps have this view across the entire Kubernetes node. And not only does this allow us to see things like or associate networking with Kubernetes identities, it also allows us to be really efficient. So this is a kind of complicated looking diagram of how container networking traditionally works in Kubernetes. So every pod is created with its own network namespace, and that means it has its own TCP/IP stack. And there's also a TCP/IP stack on the host that all the pods are running on. And because the pod is isolated from the host networking with its own network namespace, it has to make a network connection to the host in order to communicate with it. And that's what this VF pair in the middle here is. That's how the connection between networking inside the pod and networking on the host, they're connected together. Now, because there are two TCP/IP stacks, that means whenever a packet arrives at a pod or leaves a pod, it's got to traverse both of these stacks. And although that's a fast operation, if you're sending millions of packets or receiving millions of packets, traversing two stacks does add some overhead. With an eBPF-based networking solution, we can be a lot more efficient because we know through the fact that we're using eBPF to observe network activity, we are assigning IP addresses to pods from inside Cilium. And we know which IP addresses are assigned to each pod, which virtual Ethernet connection is associated with each pod. So we can basically direct packets immediately either to the pod they're destined for or to the outside world through the external Ethernet port without having traversed the whole TCP/IP stack, essentially replacing a lot of that stack with eBPF. So we can send a packet that comes onto the host. We can look up the endpoints. I showed you the endpoints in the CLI earlier. We can look up that endpoint and send it directly to the virtual Ethernet interface where it gets handled by the pod's networking stack. And if we look at a flame graph for where time is being spent when a packet is received, we can actually see that some time gets spent for a packet that arrives on a host. It spends a bit of time in the eBPF stack, and then it moves into the pod's networking namespace, spends a bit of time in the TCP/IP stack there, and then gets read by the socket inside the pod. Now, this flame graph is just one small piece of data from a large networking benchmark exercise that we've done recently, and there's a link there to a blog post. If you want to dive into all the details of network performance, there's a lot of information on that blog post. But one of the main learnings, if not the main learning from that whole benchmarking exercise, is that eBPF really dramatically speeds up networking. So this is an example of a performance graph that we measured. The blue line is just node-to-node networking. So no containers involved, just regular TCP/IP stack on two hosts communicating with each other. And we're looking at the round-trip request response throughput. So the higher the graph, the faster the throughput. And the red and orange bars are two different eBPF-based networking solutions. And the yellow and green ones are, well, one of them has eBPF turned off, and one of them is a non-eBPF-based solution. As you can see, the eBPF bars are almost as fast as not having container networking at all. So we can achieve nearly the same throughput with eBPF-based container networking as with node-to-node networking. This is really here to show how eBPF is changing the face of networking, because the performance is better in changing the face of container networking, because the performance is better than IP tables-based solutions. Again, eBPF applications have this view across the entire node. And I just want to drill down a little bit further into this, because what it means is you don't have to change anything about your application or anything about the way your applications are configured in order for eBPF instrumentation to work. And I think this idea was very neatly summarized by Nathan Leclerc in this little diagram, little kind of bumper sticker that he put together. My other sidecar is a kernel. So let's just have a little think about what the sidecar model means. A lot of observability and security tools today work by injecting a sidecar container into each application pod. Things like logging, it's very common to see configuration adding the logging component into a pod. Now, you might explicitly configure that in your pod definition, or that YAML might be added automatically for you. Sometimes there's pre-processing for all your pod definitions that injects the sidecar YAML, the containers for your sidecar into every pod, or it can even be done dynamically using admission control. Even if you're not manually changing your YAML to add a sidecar, the definition is being changed before it actually gets deployed. So what you deploy in your production environment includes this additional configuration for the sidecar container. So what happens if somehow that YAML injection is missing or goes wrong? Well, the answer is if your sidecar isn't defined in your application pod, then the sidecar won't be there. So you can end up with pods that are potentially not instrumented if something went wrong with that YAML configuration. Or if something malicious happened, if you had an attack going on, one of the things that your bad actor might be trying to do would be avoiding having a sidecar inside a particular pod so that they can carry on doing whatever it is they want to do as part of their attack without being observed. Because if the sidecar isn't there in the sidecar model, the observability isn't there. And this is really why eBPF is super powerful for observability. We don't need the sidecar. We don't need any application changes because all the events are in the kernel. They're triggered by events that are going to happen in the kernel, irrespective of your application and irrespective of how it's been configured. So you don't need any application changes, and your instrumentation will work across everything that's happening across the entire node. These superpowers are already being used by several different applications and projects across the cloud native space. I've already talked a bit about Cilium as a networking tool that takes advantage of eBPF. You might have come across Falco, which is a security tool that uses eBPF to observe events that are suspicious in some way, that match a signature of something that you wouldn't expect to happen under normal circumstances. Tracy is another similar application from my former colleagues at Aqua Security that's also using eBPF to spot malicious activity in a slightly more lightweight way than the way Falco is doing it. And I mention it because it lets you define the security events in Rego, which is the open policy agent language. And then there's the new kid on the block, which is Pixie, which is now part of New Relic. And it just got open sourced and has applied to the CNCF as an observability tool, again, using eBPF to observe events across your whole cluster. So I just wanted to give you an idea of how eBPF can provide security information with something that we've been working on at Cilium. You already saw in my first example, in my Hello World example, that we could very easily get hold of process information that related to an event. You've also seen how we can tie event information to Kubernetes identities. If you put those two things together, you can start to observe which process was responsible for example, network activity. In this example, we can see not just exactly which pod was responsible for network connections, but also which executable under which process ID made those network connections. So in this example, the two network connections are to places that are expected. But imagine that one of these network connections was to a cryptocurrency mining pool, for example. That would be a highly suspicious event, and it would be very easy to detect with eBPF-based observations like this. You would have all of the clues at your fingertips that would allow you to track back what had happened, which executable was responsible, and how a compromise had happened, thanks to the power of eBPF. So we've seen that eBPF lets us write custom code to run in the kernel. And because there's one kernel per host, eBPF gets visibility into everything that's happening on that host. So far, I've talked exclusively about Linux, which is the operating system that's come to dominate the cloud native ecosystem running containers in the cloud. But there are other operating systems too. So it's pretty exciting to see that Microsoft have announced eBPF on Windows. So this is a project bringing eBPF technology into the Windows ecosystem. Things won't be exactly the same because the kernel data structures aren't the same in Linux and Windows, but this is bringing as much eBPF conceptually and tool chains from the Linux ecosystem into the Windows ecosystem. So that's an exciting project to keep an eye on. And I think it goes to demonstrate how important eBPF has become and will be for building these kind of networking and observability and security tools. So if you want to find out more about eBPF, there is a site, a community site at ebpf.io. And there's a lot of background information there and listings of eBPF-based projects and some pointers to how you can get started writing your own eBPF programs. I've also listed the Cilium website and, of course, Isovalent. If you would like to learn more about Cilium, there's also a Slack channel that you can find on the Cilium website, and the team is always very happy to help with questions. So I hope there will be some questions from you here at Craft Conference. So with that, I'll say thank you very much.
Amazing. Thank you very much, Liz. Amazing. I learned this whole thing is very new to me. And I would like to remind all the viewers to ask questions in the Q&A and rate the talk. I rated 5. And we have one question from Yulia. I'd like to just talk about this because I think just to, clarify this, you have introduced 2 things here. You have introduced eBPF and you've introduced Cilium, which I think is something built on top of eBPF, right? So my
Correct.
question, and I think it's related to Yulia's question, eBPF is something that people can use to build tools, right? And Cilium is one tool that, for example, it can be used for running apps on top of Kubernetes instead of just running them directly on Kubernetes.
So Cilium will provide the networking. When you're running applications in Kubernetes, you have to pick a networking stack. There are several that you can choose from. Cilium is one option. But it's using eBPF to provide that network connectivity. There are other tools that will be using eBPF, like Falco, for example, that would be using eBPF to look for security events. So we, in Cilium, would be hooked into lots of network-related events.
Yes. So
because there's so many different types of events you could hook into.
So basically, Cilium makes Kubernetes super powered. We could say that, right? It gives some extras to it. And eBPF, I suppose, like Yulia is asking, what are the security implications of being able to write programs to the kernel like that? I suppose these are really like tools for very specific cases, like Cilium, right?
Yes, and you should treat eBPF programs much like you would treat anything else that requires root access. So any kind of security or logging tool that you would normally run will often require some level of privileges, or at least in terms of observing other applications. I suppose with great power comes great responsibility. So yes, you need to make sure that the right to run, I think I mentioned that there is a permission or a Linux capability that allows a user to load an eBPF program. So it's called cat BPF. So in older kernels, you'd need cat sysadmin to load BPF programs. And in more recent kernels, you don't need the full sysadmin privileges. You can just have this cat BPF privilege in order to run a BPF program. But yes, it is something that you should only give to users that you trust.
I see. I guess for companies that want to run apps on the cloud, using Cilium is a great thing instead of just using Kubernetes, right? That's the takeaway we can say, right? We should use Cilium, right?
Well, I mean, I guess I'm biased, so I would certainly say yes. I think Cilium is the best option for networking and creates there's a lot of additional capabilities that you have through that we have built using eBPF. But I think broader than just Cilium, the fact that there are so many other tools being built using eBPF, and I think we will continue, we'll see more and more of them because it's such a powerful way of building tools that need this visibility across the whole system.
I see.